you won't listen, you always stay and stay. How can I miss you when you won't go away?
A guy named Markowitz, back when I was in elementary school, you can look that one up if you like, decided to look at the mathematics and likewise the graph of return, percentage profit if you like, versus the standard deviation. And given that most people tend to prefer less risk than more because losing hurts more than not gaining, came to some interesting results. Let's look at those, particularly the mathematics of the variance or the standard deviation, which is the square root of the variance. We can look at a two-asset portfolio to begin with, noting that any portfolio can be thought of as a single asset, like a mutual fund, and vice versa. A company is a portfolio of their product line. And let's say if there's two of them, well, the weights, the proportions add to 1, and the return to the portfolio is just a weighted average. Now, the variance of the portfolio looks a little daunting here. Well, you got the weight squared, the variance, and then 2 times the cross product of the covariance. I'll give you a mnemonic device. And the weight squared again of the other variance. Suppose you're doing your backyard and you want to have some different kind of layout for some tiles. And, you'd say, you have A and B ones and C and D ones, and you'd cross multiply all the combinations. But look, squaring them, that's on the right-hand side. You got A squared, B squared, that's down there in purple if you like. But notice there's 2 of the ABs. So going back, that means we can do a substitution, and it either makes it more complex or simple depending on your viewpoint. By the way, the notation here can vary. The covariance AB is sometimes written with a sigma and a double subscript. You'll see why later. So if we substitute that back in, it looks a little bit daunting, but I got some shortcuts. And you substitute that in, and the covariance is the correlation times the 2 standard deviations, which allows us to do a simplification. If the correlation is 1, then it's just the sum of the 2 weighted standard deviations squared. If the correlation is -1, then it's the difference between the 2 weights squared. Now with 2 assets, we can do a substitution, noting that, say, B is just the remainder from 1 from A. You substitute that in, and boy, look at that. And then you take the first derivative, and you solve, and you get the following. So that the weighting for a minimum variance portfolio would be the other variance minus the covariance over both the variances minus twice the covariance. Now, you may not want a minimum, but anything beyond that, as we will see, is irrational. So if the correlation is +1, then you factor everything out and you get the other standard deviation over the difference in the standard deviations. If it's a perfectly negative correlation, then you factor it out. You get the other standard deviation over the sum of the standard deviations. And if it's a 0 correlation, you take the other variance over the sum of the variances. Let's go back to our graphic. See, if let's say B is around a 1 standard deviation, A is around 2, and let's do the numbers. For a perfect positive correlation of 1, we would take, the standard deviation of B, that's 1, over, watch it, the signs do flip here, the standard deviation of B, 1, minus the standard deviation of A, 2, that's -1, into 1, -1. What's that weight mean? It means the other weight is 2, and on the graph that would actually be way down on the lower part on the axis. Think of it like maybe shorting or buying on margin. Let's do a perfect negative correlation of -1, and that formula is the standard deviation. Here, again, 1 for B, over the sum of the weights, that's 1 plus 2 is 3, and the weight would be 1/3. What's the other weight? 2/3. And sure enough, it makes that arrow touching on the axis where you have 1/3 and 2/3 in A. In the case of where you have a zero correlation, in that case you're using the variances, the standard deviation squared, and you would take the variance in B, 1 times 1 is 1, and the variance in A is 2 squared is 4, and you'd add those up and you'd have 5. So the weights there would be 1/5 and 4/5 at the minimum. We don't have to stay with two securities, and we can probably do it with computers, of course, but also we can look at it more theoretically. If there are in securities, well, that becomes a weighted average where all the weights still add to 1 and the returns are just a weighted average, and the portfolio variance becomes a square matrix. That's why we have two double summations here, the rows and the columns, and the weights in each row and the weights in each column. And we're going to use that covariance symbol with the double subscript. It's going to make things easier. Now, if we equally weight them, that means 1/nth in each and every security. Then we can do some substitutions. And notice the weights become 1/n squared. And if we visualize this square matrix, and sure enough, well, let's see, there's 1 by 1, 1 by 2, etc., all the way down n by n. And let's look along that diagonal. Notice the I and j, the numbers for the row and column, are identical. Now, what does that mean? That means it's the covariance against itself. Now, no one seems to get this right the first time, including myself. But what is a covariance against itself? It's not 1. It's the variance. So now look at it. How many variances are there? It's a diagonal. It's a square. So there's got to be n of them. How many non-variance covariants are there? Well, all of them together is n squared. Let's subtract the diagonal of variances. There's n of them. So the remainder would be n squared minus n. Let's see what that does. So let's again look at our double summation matrix, separating out the cases where I equals j and I does not equal j. And when there's I equals j, there's just I of them. And again, the weightings are 1/n squared. And there's now times the variance. Now for the cases where we still have I and j matrix, again, the weightings are 1/n squared. And there's that covariance notation. Now how many of them are variances? N. And what's the weighting? N squared. Now, in the case of the covariances, instead of saying n squared minus n, we could say n times n minus 1. This provides a profound result, which is, as n gets big, approaches infinity, let's say, a big number, the first term is n/n squared approaches 0. The second term approaches 1. So, as n gets big, the idiosyncratic risk, the variance of each individual security, becomes meaningless. 0. And the other relationships, the covariance, the market, if you like, just approaches 1. This is a mathematical proof for diversification. And it also means if you do so, you don't have to pay attention to the individual company news, which sure takes a load off your back, in that case with DrCinvests.